Okay, so today we will see the mutual inductance between two long coaxial solenoids. Okay, so here I have one solenoid, okay, one bigger solenoid, so like this. Like this I have. Okay, so inside that I have one more solenoid, so that also having the coils like this. Okay, so this I am taking A2 and this I am taking A1. Okay, so the length for the solenoid is same. Okay, the length for the solenoid is what? Same. And this I am taking solenoid 1, that big solenoid I am taking solenoid 1. So and I am denoting it with N1 turns. Okay, N1 turns. And I am taking the smallest solenoid as 2 and I am denoting it with N2. Okay, so this is the common axis, which is nothing but the common axis for the two solenoids. Okay, so first now we will start seeing what is happening within this setup. Okay, so when I am taking the first solenoid, okay, so this will produce some magnetic field lines, and this field lines will come closer to the second solenoid, and this field lines will be linked to the second solenoid, which is nothing but the area 2. Okay, so now when I pass the current, okay, the magnetic field will be produced in the solenoid. So that is the common form we have for that. What is that? B is equal to mu naught Ni. So we have derived this in the third unit. Okay, we have derived this equation in the third unit. So this is the equation when you are passing the current. Okay, the magnetic field will be produced in the solenoid. So this is the general form. B is equal to, which is nothing but magnetic field is equal to mu naught Ni. Okay, so now what is meant by electric flux? So here I will have the magnetic field lines, and this field lines is going to be crossed in a selected area, so which means there I will be getting the magnetic field lines. Okay, so when I have the solenoid like this, inside the solenoid I will have the uniform magnetic field. Okay, I'll have the uniform magnetic field inside the solenoid. Outside the solenoid I'll not have the uniform magnetic field. Okay, so now I'm going to check only for the A2. Okay, A2 means, which means I'm passing the I'm getting the magnetic field in the A1. So that magnetic field is going to enter into the A2, which means it's going to linked. Okay, going to linked in the A2. Okay, so how I can write this equation means, so before that we'll see the magnetic flux formula. Magnetic flux is equal to integral of B dot A. Okay, with the vectors. Okay, this is the magnetic flux general formula. Okay, so now this number 1 turns, which means the number 1 turns means the field lines produced in the area 1, okay, it's going to link with the N2. So which means I can write the equation, okay, like this. Magnetic flux in the area 2 due to the 1. Okay, which means the magnetic field lines, when it passes through the selected area, I'll be getting the magnetic flux. Okay, so 2 is equal to B dot dA vector. So dot product, we know that what is dot product of two vector is what? Yes, integral B dA cos theta. BdA cos theta. Okay, so in this case, I will have the magnetic field lines like this. I'll have the magnetic field lines like this. So which means I'll have the parallel magnetic field lines. So which means here I don't have any angle. So I can take this as a 0 degree. So cos 0 degree is equal to 1. Okay, so cos 0 degree is equal to what? 1. So now I can change this equation. Okay, before that here I have the field lines entering only into the A2 area. So I am mentioning the A2 here. Okay, va? So now this magnetic flux 21 is equal to, so now this equation will be changed into how? B, because cos theta is equal to what? 0 degree. It will be 1 only will come. So flux, okay, magnetic flux into, okay, due to 1 is equal to BA alone will come. So now we are seeing for B is what? B1 means magnetic field lines is going to the second area. So B1, A2. Okay, so now just now I have seen the equation, general form for mu naught Ny. I am taking this as an a B1. Okay, so just substitute the value magnetic flux to 1 is equal to, what is the B1 value? Yes, mu naught Ni. Yes, N1, I1. I'll be mentioning N1, I1 because the number of turns and the I1, the current I1. Okay, mu naught N. Yes, N1, I1 and this A2. This A2. Okay, so this is only for single turns. This is only for single turns. Okay, when I see for number of turns. Okay, when I see for number of turns, what will come? N2 is N2, the magnetic flux 21 is equal to, here I will get the what value? So what does mean by N? N is equal to what? Small n and L. So already we have seen this formula. N is equal to NL. Okay. So this is the general form. Now I am changing it according to the numbers. So number of 2 means, N2 means what? The number of turns produced in the coil N2 and the magnetic flux 21 is equal to what? N L. So you can able to understand, I think, why I am mentioning N L here. So N2 is equal to, yes, N L. So here for which we are checking N2 only checking. So here also you have to mention the number 2 only. You should not mention N1. And the same equation as it is. N1, I1 and A2. Okay, N1, I1 and A2. Okay, hope you will not have any doubt here. And again, I'm going to take this N1, L, mu naught, N1 and A2 as a mutual induction. So why I'm telling this is a mutual induction means, so here I'm passing the magnetic field that entering into the coil, the solenoid 2, okay, which is nothing but the A2. So in this case, this is the mutual induction produced by the area 2 due to this A1. So I'm taking this as a mutual induction. Okay, so this is a mutual induction. So this is the form they have given in your book. Okay, so this mutual induction, it always depend upon the permeability. Okay, this mutual induction, it always depend upon this permeability. So only they have mentioned the mu naught here. So remaining and all, as per the diagram, we have derived the thing. Okay, so now we'll see for the second solenoid. Okay, now we'll see for the second solenoid. So here the solenoid 2. Okay, so here what I'll get? The magnetic field 2. Okay, the mu naught, because the mutual induction, it depends upon the permeability. Okay, and the number 2 and the I2. Okay, so first I have taken the equation like this, which means mu naught N1 I1. So now I'm checking for the area 1. So I need to take the solenoid 2, because the mutual induction I can see only in the area 1. When I am looking for the solenoid 2, the mutual induction will be produced in the area 1. When I am seeing for the mutual induction in area 2, so the magnetic field lines is coming from the area 1. Okay, so solenoid 2 means B2 is equal to mu naught N2 I2. Okay, so now I can change this equation. Magnetic flux 12 is equal to, what is the B2 value? B2. So before that I'll write this formula B2 A2. So here also I have mentioned the A2. Why means I'll explain now. See, so first we'll take only the inside magnetic field lines. Why means the inside magnetic field lines only will be uniform. Okay, so now I'm going to check for the second solenoid. Listen carefully. I'm going to check for the second solenoid. In this also I will have the magnetic field lines in this direction. Okay, and I'll have the outer side, I'll have one solenoid. So here we didn't consider inga produce agra and the magnetic field lines we are not taking in the consideration. We have taken only the inside magnetic field lines. Why means inside only we will have the uniform magnetic field. But in this case, when I look for the second solenoid, here also I will have the magnetic field lines outside. Okay, which means in the first solenoid. Okay, in the first solenoid. Okay, in that case, I'll not consider the first solenoid magnetic field line. So when I compare these two solenoids, inside, okay, the second area 2 only, I will have the uniform magnetic field lines. In this case, I will not have magnetic field lines will be same. Okay, the uniform magnetic field lines will not be produced in the area 1 when I'm checking for the area 2, because here I have some spaces. Okay, but here I don't have any spaces between these solenoids. So here I'll have the uniform magnetic field lines. Okay, so only in this second solenoid also I'm mentioning the area 2, because the field line is going in this way only. Here I have more space, here I have only less space. Okay, so now B2 A2. So magnetic flux 1 2 is equal to, what is B2? Yes, mu naught N2 I2. Okay, so this is the magnetic flux 1 2. Okay, which 1 2 it defines as what? Magnetic flux in 1 due to 2. Okay, but the area will be 2 only. Okay, I have explained you why I have written A2 here. Okay, now when I look for number of turns, the same method only. Number of turn means here N1 will come. Here what will come? N1 will come, and this magnetic field 1 2 is equal to here N1 L. Okay, NL. So I have written here like that. N2 L I have written before solenoid 1. So here I am writing N1 L, and the same equation mu naught N2 I2 and A2. Okay. So in this case, this is the mutual induction. Okay, this is the mutual induction produced in the area 1, which means the first solenoid due to the second solenoid 2. Okay, so this and this will be equal. Okay, this and this will be equal. Okay, so this is the mutual induction between the two long coaxial solenoids, which means the length will be same, but inside the solenoid only will have the uniform magnetic field. Even though if I have the bigger solenoid also, there will be no uniform magnetic field. So inside the small solenoid only I will have the uniform magnetic field. Okay, so the space is important. So this is the mutual induction between two long coaxial solenoids. So if you have any doubts, you can contact me. Okay, thank you.